Hello guys, this is Code and Code and this is 20th lecture of this graph theory series part 1. In this lecture we are going to study about BFS on 2D grid. We will be also implementing the algorithm that we will be studying in this lecture. So what are the lecture goals? Of course the lecture goals are to understand BFS on 2D grid with some examples, with the help of some examples. And then of course we'll be looking at the similarities between BFS on a graph and BFS on 2D grid. This is same as what we did in the previous lecture when we have studied DFS on 2D grid. There also we have seen that there are some similarities. In fact, there are many similarities between when we apply DFS on 2D grid and when we apply DFS on graph. Same way, there are many similarities when we apply BFS on graph and BFS on 2D grid. So we'll be studying those as well. And of course, finally, we'll be implementing the algorithm that we just studied. So if I show you the example, suppose this is the example 2D grid and we have to apply BFS on this grid where this cell is actually your starting point. And we are assuming that common edges are sides. So from here you can move here, from here you can move here, but from here you cannot move here because these two cells do not have any common edge. Now one more thing, if you haven't following this DFS graph algorithms on grid part from starting or from beginning, I would highly advise you to go and watch those lectures first, where we have introduced BFS, DFS and other algorithms of graph theory on grid. So I highly advise you to watch the introduction lecture first, because there are many things that I have explained there and I cannot repeat those things here. So make sure you have watched those lectures first. Now if you have to apply BFS from here, assuming only you can move from a cell to only up, down, left and right, that means you can move from a cell to any other cell which is having a common edge, then the BFS result would look something like this. This is the source cell, so distance of this cell would be 0, right? From all these cells can be reached in one step. That is why all of these cells are at distance 1. These are at distance 2 because to reach from this cell to this, either you can go this way or this way. Similarly, these two are at 3 distance because either you would go this way or this way or this way. Anyway you take from here to here will take 3 unit of time, 3 unit of steps minimum. So that is why the distance of these cells from source is actually 3. If I show you another example where now common sides as well as common corners are considered to be edges, that means from this cell you can move to up, down, left and right, as well as to these corner cells. From here you can move here now. So basically from here you can move in all 8 directions. So if you apply BFS considering this cell as your source cell, then the BFS result look something like this. This is at distance 0, this cell is at distance 0 from source cell. Of course these all are at distance 1 because you can reach any cell out of these in 1 unit of step. For example, from here you can reach here by simply you can move from here to here, because now you can consider these two cell adjacent, because now we are considering corner cells as adjacent cell as well. You can reach this cell in 2 steps or this cell in 2 steps. You can go from here to here and then here. So this is what BFS result would look like if we consider all common edges and as well as common corners as edges. Then this would be the BFS result. The question is how we'll apply BFS on grid. But before that, let's see how we apply BFS on simple graph or any graph. To do that, we have certain source vertex from where we start, and what we do, we create a queue and we insert that source vertex in that queue, and then we initialize the distance of the source vertex to be 0, and also mark the source vertex to be visited. 1 means visited, 0 means unvisited. So basically we are assuming this to be source vertex. So what we have done, we have inserted this into the queue, mark its distance from source to be 0, and also marked it as visited. After that, while queue is not empty, this whole algorithm I have already explained how BFS is applied on graph theory series part 1 course as well. So if you have no idea how BFS works, so first I would advise you to go watch those lectures. So after doing that, we run a while loop while there is at least one node in the queue. We take out the front node, and we also pop out that. After that, for each node which is adjacent to current node, we'll see whether that node is visited or not. If that is not visited, we would insert that node into the queue. We'll also mark that node as visited and also initialize the distance of that node to be distance of current node plus 1. So basically distance of these two nodes would be distance of this node plus 1, which means 1. So this distance of this and this node would be 1. Similarly, distance of these two would be 2. So this is how normal BFS works. Let's see how BFS on grid works. This is the code for BFS on 2D grid, and this is of course the code on graph. Now we see, as explained in the introductory lecture, as there are nodes in the graph, there are cells in the grid, right? So here we would have x and y, because now we need to have the coordinate the coordinate of the source cell. So source x and source y are the coordinate of your source cell. After that, you would insert in queue those source coordinate, because now here while we are working on graph, each node is designated or assigned a single integer that defines that node, like node 1, 2, 3 or 4. But here a cell is uniquely identified by number row and column number of that cell, and these are this represents the row number, this represents the column number. That is why we cannot have only one, but we would have two arguments. So we would insert that cell into the into queue. We would mark it as visited and also initialize its distance. Now see here, queue would contain a pair instead of a single integer. This queue would now store pairs, and this way you can make pair in C++. Just put them into in curly braces. Now these three steps are similar to what there are three steps in BFS on graph. Now again same thing will run while there exists at least one cell in the queue. After that, you take out the current node, but here we would take out the current cell, which is represented by x and y coordinate. So we would take out x and y separately. So q dot front actually represents the pair, but I only want the x, so I would access the first and I would access the second for y. And now of course we would remove that cell from the queue. After that, here we access the adjacency list of the current node to see if there are any node which are adjacent to current node which are not visited, right? This is what we are checking, and then we are performing these three steps. But here we already know for a cell there are either 4 adjacent cells or 8 adjacent cells, depending upon whether we are considering only the common edges or corners as well. So there can be 4 to 8 different adjacent cells. Depending upon that, you would have either 8 or 4 different directions. So here I'm considering only 4 different directions. Here this I have already explained what is valid function. You would see, and is valid function dx and dy I have already explained in the lecture where I have taught DFS on 2D grid. So that is why I'm saying, if you are not following this graph algorithm on grid from beginning, just go and start from the beginning, because there are many things I'll be referring from those lectures. So this is valid will check whether the new cell you want to step on is actually valid or not. This would basically check whether the new cell you want to step on is actually visited or not, and also that cell exists or not. For example, for current cell you can try to go up, but what happens when you are on the first row? When you are on any cell on the first row, the cell above that, the direction up doesn't exist. That is why this valid function will take care of everything. So if the new cell you want to step on, which is current x plus dx of I, current y plus dy of I, dx and dy array I have already explained in that lecture where I have explained DFS on 2D grid. So go check out those lectures if you have no idea about this. So this would be the coordinate of new cell you want to step on. So this would check whether that cell exists or not, and also if that cell is visited or not. If this function returns true, that means this is a valid cell, so you can move on to that. In that case, what we would do, we'd simply calculate the x and y coordinates of the new cell and simply assign the distance of new cell to be distance of current cell plus 1. We will mark that will mark the new cell to be visited, and also will push the new cell coordinates into the queue. And this is how BFS on 2D grid works. This is exactly the same as BFS on normal graph. So I don't think if you have studied normal BFS on normal graph, I don't think you will find this algorithm, the new algorithm, even a little bit difficult. So if I show you the code and a working example, this is the code. This is the isValid function that checks whether the coordinate of new cells are correct or not. Before that, this is a distance array which will store the distance of every single cell after BFS. This is to take care of whether the current cell is visited or not, and these are the dimensions of the grid. So if x is less than 1, or x is greater than n, or y is less than n, or y is greater than m, basically this is checking whether the current cell is inside the grid or not. If you are going outside, we would if any of the condition is true, and if any of the 4 condition is true, that means you are going outside. That means we would return false. If that doesn't happen, that means the cell you want to go is actually a valid cell which is completely inside your grid. In that case, we would see whether the cell is actually visited or not. If this is already visited, we would return false, because we can't visit an already visited cell, right? That is why in that case we would return false. If none of these 2 conditions are true, that means the cell you want to visit is actually unvisited and exists inside the grid, so that is why we would return true. This is the direction array I have defined, dx and dy. These 2 combined will form up, right, down and left. Again, this I have already explained in the slide, so the same algorithm, just this is what I have added extra. This is to print the distance array. So how algorithm works? Simply we would read n and m, which is dimension of the grid, and after that we would read x and y, which is source cell for BFS. And finally, after performing BFS, we are printing the distance array. So let me show you. If suppose we have 4x4 array and the source cell is 1 1, so this is your distance array. So source is at distance from itself. These 2 cells are at distance 1, these are at distance 2, these are 3, 4 and 5 and 6. So now let's take bigger example, say 9x9, and I'll be starting from 5x5. So you see, this will be your starting point, and this is what your distance array would look like. So this is how you apply BFS on 2D grid. In the next lecture, we'll be taking some of the interesting examples and solve some of the problems using the same algorithm, so that you feel confident about implementation of this algorithm. So this was all for this lecture. If you have any doubt or query, ask on the article that I've created for this course on discuss.codechef.com. I'll be putting the link to the article in the description of this video. So if you have any doubts, you can ask there. So this was all for this lecture. Thank you guys for watching. Until the next video drops, keep coding. Thank you.